Bismillahirrahmanirrahim. In today's video lecture we will talk about digital encoding schemes or binary voltage encoding. These schemes are in the form of non-return to zero, non-return to zero inverted, Manchester encoding. We have differential Manchester, 4-bit 5B, which is normally used in fast Ethernet. So these schemes are used to encode binary data into signals. And as we know, binary data, we have only two choices. We can use 0 or 1. So we can assign different voltage level to binary ones and zeros. And non-return to zero, 0 is represented by a low signal and 1 is represented by a high signal. So we can use either low and high voltage level. And voltage doesn't return to 0 between the bits. So you can either use 0 level or positive level, and we don't see any middle point. So let's start. For 0 we have low voltage level and for 1 we have high voltage level. So this is the most simplest schemes. However, there are some problem associated with non-return to 0, and these schemes are transmitting consecutive 0 or consecutive 1s. If you are transmitting consecutive 0 or if you are transmitting consecutive 1, so it may cause some problems, because if you are transmitting consecutive 0, so you will be always at the low level, and if you are transmitting consecutive 1, so you will be always at the high level. So both may be cause some problems, and these problems are in the form of no signals and baseline vendor. Because if you are transmitting consecutive 0 or low signals, so that may be intercepted as a low signals, and it would be constantly at low level. And due to consecutive 1s, another problem that is called baseline vendor may occur. Baseline vendor is basically at receiver end, the distinguishing threshold goes down or goes up, so that may also create problem while transmitting any signals. NRZ scheme is normally used with serial port communication. However, most of the problems in digital encoding schemes are associated with non-return to 0. And the third problem is unable to recover clock. As we know, the digital transmitter sender clock and receiver clock should be precisely synchronized, because receiver job has to generate clock from the transmitting data, and every transmission or transition between low to high or high to low synchronize it would with clock. If there is a transition, that is the signal either constantly on the high side or constantly at the low level, so the receiver may fail to synchronize the clock, and due to this mismatch of clocking between sender and receiver, there is a high possibility of data lost. So in the timing diagram you can easily see sender clock and receiver clock. If sender clock is fast and constantly comparatively to receiver due to certain reason, then receiver clock may skew and may leads to miss 1 bit. So in order to overcome this problem, another scheme called, or we can say alternative schemes for NRZ is are available in the form of non-return to 0 inverted. In this particular scheme, you can make a transition from current signals switch voltage level to encode transmit of 1. So you always make transition at 1 and stay at current signal, or maintain level at 0. So we can solve the problems of consecutive 1s. So because you are making transition at 1, it means that at every one you are supposed to make transition. So we can overcome the problem of, or we can say we can overcome baseline vendor problem easily through non-return to 0 inverted. However, there is another scheme called Manchester, which is comparatively better scheme. We can overcome both the problems, even consecutive 0s and consecutive 1 in Manchester encoding, because in this particular scheme you can make transition at 1, or you can also make transition at 0. So both the bits may be used for making transition, and you can state you can state the signal state from high to low and low to high in Manchester encoding. So here 1 is used for high to low and 0 is used for low to high. And however, there is some certain problem, because half bit per transition, or we can simply say you can transmit 1 bit between 2 half cycles. So there is a trade-off between all the problems and with the efficiency. So you are not properly utilizing when this is 50% efficient comparatively. This scheme is normally used in 802.3 standard, or we can say simple Ethernet. So we have another scheme that is called okay, these are the timing diagram for both these schemes. For NRZ, we already discussed this, and NRZI you can make change and transition always at 1, so whenever 1 for 1 you can make transition. However, Manchester encoding, 0 is for low to high and 1 is for 0 is again low to high, 1 is for high to low, and then you can make this timing diagram. In the next video I practically demonstrated these schemes. Another scheme that is called 4-bin 5B scheme, which is normally used in fast Ethernet. In this particular scheme, every 4 consecutive bits of data encoded in a 5-bit code symbol. So 4-bit pattern is translated into a 5-bit pattern, and not additions. However, there are 80% efficiency with these schemes, because 4-bit are data bit and 1 is extra bit. So that's why out of 5 bits 4 bits are useful bits, so that's why it achieves 80% efficiency. However, there are some guidelines associated while making bit patterns. The first guideline is that no more than 1 leading bit and no more than 2 trailing zeros. So in a bit pattern, any bit pattern started from 2 zeros will be considered as an n-valid, or any pattern that ends with 3 0 will be considered as an n-valid. You can use only 1 bit at the starting and only at least or at most 2 bits at the end. So you can use 3 bits out of 5 bits. That's why you never get more than 3 ones consecutive zeros. So we can overcome consecutive zero problems with 4B and 5B encoding schemes. In the next video, I will practically demonstrate these schemes, that how can we encode a binary data through into digital signals using NRZ, NRZI, bipolar AMI, Manchester encoding, differential Manchester encoding. Thank you.